Something really strange, kind of counterintuitive, is happening in robotics right now. We're seeing this whole new wave of robots doing these incredible things. But the secret to their success? Well, it is definitely not what you'd think. Okay, let's get into it. And that brings us to the absolute heart of the matter, the big mystery we're going to unpack today. How in the world can a model that has zero concept of physics, it's literally never heard of Isaac Newton, control a physical robot in the real world? I mean, it sounds like it should be impossible, right? But it's happening. And look, this isn't some lab experiment. This is out in the wild. You've got Unitree's G1 pulling off these mind-bendingly complex movements. Figure AI has robots on the factory floor at BMW right now. There's a robot from Physical Intelligence that can fold your laundry. Heck, even the legend itself, Boston Dynamics Atlas, is starting to switch things up and use these new methods. So what's the one thing that connects all of them? Well, it's this simple and honestly kind of shocking idea. They've given up on trying to understand the world through physics first. They're taking a totally different route to get things done. This really sets the stage for a story about two competing philosophies in robotics. You can think of them as two separate tracks that have been running in parallel for 30 years, but right now, they're finally having their big showdown. So on one side, you have the classic physics track. The whole idea here is model first. You sit down, you write out all these elegant equations to describe the world, and then you use math to figure out the best thing to do. On the other side, you have this new kid on the block, the VLA track. That stands for Vision, Language, Action. Its philosophy? Forget modeling. Just learn from data. It doesn't care about equations. It basically does what ChatGPT does, predicts the next token, except its token is a robot action. It just goes straight from seeing to doing. And the physics track has a really long, really impressive history. I mean, it started back in the 70s with the math that let robots like Asimo walk, even if it was super slow. Then we got breakthroughs in dynamic balance. By the 2010s, a technique called Model Predictive Control, or NPC, was the gold standard. That's what powered Boston Dynamics for years. But this whole approach eventually hit a wall, a fundamental limit. Its performance could only ever be as good as its physics model. And eventually people started needing to plug the holes with neural networks. And this quote just hits the nail on the head. The performance of these traditional physics-based methods eventually just flattens out. It hits a ceiling. Why? Because your model is only as good as a human's ability to perfectly describe the messy, chaotic, real world with a bunch of clean equations. And here's the kicker. You can't just throw more computer power at this problem to fix it. The model itself is the bottleneck. Okay, now let's flip over to the VLA track. It started out with this simple idea of just copying humans, which was, well, kind of flawed. But then, just a couple of years ago, things exploded. In 2022, Google's RT1 proved that the same scaling laws that make models like GPT-4 so smart also work for robots. A year later, RT2 merged a huge internet model with robot data, and suddenly the robot had common sense. And now, in 2024, we're seeing powerful open source models and super fast control. The pace is just blistering. So why? Why is this brute force data-first approach suddenly taking over? Well, the answer, believe it or not, has less to do with robotics and more to do with information theory. It all comes down to what I like to call the compression secret. Okay, so what is compression? Super simple. It's just about encoding information using fewer bits. And here is the big idea. Writing a physics model is a form of compression. You are taking the infinitely complex real world and squeezing it down, compressing it into a handful of elegant equations, like F equals m. Now, this high compression approach has a massive trade-off. It's really efficient for simple things, like figuring out a rocket's trajectory, but the very act of compressing means you are throwing information away. You're ignoring all the messy details, the friction, the way an object might bend, the temperature in the room, and because of that, your accuracy is forever limited by how good a human was at creating that simplified model in the first place. The VLA approach does the exact opposite. You can think of it as a no-compression strategy. It doesn't try to simplify reality at all. It just uses a giant neural network to learn the direct, messy, unfiltered connection between what it sees and what it does. So its accuracy isn't capped by human understanding. It's only limited by how much data and how much compute you can throw at it. The potential ceiling is just way, way higher. And this isn't just some abstract idea. I mean, look at this. When Google took a giant model trained on the internet and then just fine-tuned it on robot data to create RT2, they saw a 3 times improvement in the robot's ability to handle new tasks it had never ever seen before. That's what happens when you don't throw away all that rich information about the world. So, does this mean physics models are basically useless now? No, not at all. The reality is a lot more interesting than that. Let's take a look at how this is all actually playing out in the real world. Here's a really simple way to think about when to use which method. It just comes down to two questions. How complex is the system you're dealing with, and how much data do you have? If your system is simple, like a SpaceX rocket, and data from launches is rare, a physics model is absolutely perfect. But if you have a ridiculously complex system interacting with a chaotic world, like a self-driving car, and you have tons of data, then the VLA, learning-based approach, is a no-brainer. And if you just look at the robotics industry today, you see companies placing their bets all across this spectrum. Boston Dynamics is going hybrid, putting new AI on top of its classic physics control. Figure AI is using a layered approach, a big, slow brain for thinking, and a small, fast one for acting. Physical Intelligence is going all in on a pure VLA model. And of course, Tesla's full self-driving is probably the most famous example of a pure vision-to-action model out there. Now, it is so important to understand that this VLA approach is not some kind of magic wand. It's not a silver bullet. It comes with its own very real, very tough set of challenges that still need to be solved. We've got to be real about where it stands today. First, precision. These models still have a hard time with tasks that need millimeter-level accuracy or very delicate force control. Second, safety. It's a black box, right? We don't always know why it does what it does, which makes it a nightmare to certify for something like surgery. And third, they're not great at long-term multi-step planning, like figuring out all the steps to tidy up a messy room. So what's the big takeaway from all of this? It's not this simple story of physics versus AI. It's way more nuanced. It's about a new, more sophisticated way of building robots, where we're learning to pick the right tool, the right level of compression for the right job, based on the problem's complexity and the data we have. And that kind of leaves us with one last huge question to chew on. For decades, the limit of robotics was human understanding, our ability to write down the equations. The new limit is just data and compute. So you have to ask yourself, what happens when those two things basically become